All right. Thanks, everybody, for coming. Let's go ahead and get started. So my name's Anthony Liguori. I'm a senior principal engineer within EC2. I've been at Amazon for about 4 years now. And I've been the engineering lead for the Nitro project, which Peter DeSantis announced last night in his Tuesday Night Live keynote. And this is the hardware and software system that actually has been powering many of our instance types over the last 5 years, but really has culminated in the launch of some recent instance types like the C5 instance, which we launched earlier this month. Thank you. The M5 instance that we launched today, and then the i3.metal instance type that we announced last night. So I'm going to be talking about how we build all of these things and what's coming in the future. I've worked on virtualization almost my entire career. I am a huge geek. This is going to be really technical. I'll make sure to leave time at the end to ask questions if you have any. If you want to geek out afterwards about any of the topics we've covered, I'd be more than happy to. It's the stuff I live for. So we're going to cover the Nitro project. We'll talk a bit more about it. But to really understand the project, and note I'm describing it as a project because it really involves a lot of different things. We have to do some background on virtualization, so I'll walk through how most other types of virtualization systems work to sort of tee up how we think about Nitro. As I mentioned, we've been actually working on this for the last 5 years, and I'm going to walk through the evolution, all of the things we've changed incrementally to get to the point that we're at today. And then finally, I'm going to spend some time talking about compatibility, some frequently asked questions, and then what's coming next. So in case you didn't see the announcement last night, Nitro might be a totally new word. It wasn't mentioned at all in the title of this talk or the abstract. When we launched the C5 instance type, one of the things that we mentioned, and we didn't really put out that much information when we mentioned it, was that it was using a new hypervisor. Obviously, this is something we've put a lot of thought into and a lot of work into, as we've been using the same hypervisor, at least, for the last 11 years. Well, Nitro is this new hypervisor. This is the internal code name that we've used. This is the name we're going to use publicly. But it's really more than just a hypervisor, and that's what we're going to talk about here today. So let's step back a little bit. To really understand what Nitro is, we have to sort of understand what virtualization is and how it works. The thing about virtualization is that there's lots of nomenclature out there, and oftentimes, at least in my opinion, it's used incorrectly. People talk about things like VMM, type 1 versus type 2, hosted, device models. A lot of it's super confusing. So my real goal of these next few slides is to standardize the nomenclature so that when I talk about a device model, we're all talking about the same thing. But virtualization itself is actually conceptually very straightforward. All software, it doesn't matter if it is JavaScript executing in a web browser, whether it's a Lambda function running in the cloud, or if it's a low-level kernel driver that's part of Windows or Linux, it all ultimately consists of a series of instructions that the processor executes and some data for those instructions to manipulate. So that really is all computing. It doesn't matter what framework you're using, what language you're using, it all comes down to these instructions. And the real kind of fundamental question behind virtualization is, if we take an entire server, all of the instructions that are running on that server, and we try to nest it, we try to run it as an unprivileged process in another operating system, what happens? Can we make it work? What are the requirements to make it work? And that is really what virtualization is all about. I suspect this is the only talk at reInvent where there's going to be assembly on slides. I'm very proud of that. Hopefully you all are okay with that. It's not important to understand the instructions. Don't try to worry about rationalizing how this all works. We're going to walk through it. For the most part, assembly is actually really simple. The various instructions do exactly what they say they're going to do. So if there's an add instruction, it's doing addition. There's really no sophistication behind it. This is actually real code. These are the first about dozen instructions of the Xen hypervisor. So when you run Xen on a physical server, these are the instructions that are getting executed as soon as the server actually starts up. So if we took this instruction stream and we tried to run it on, say, your Ubuntu laptop as an application, what would happen? Let's walk through that. Let's actually see what would happen. So that very first instruction is a jump, and it does exactly what you think it would do. It does a jump. It moves the instructions forward. In this case, it's jumping forward one instruction. There's a really important reason for that, but we won't get into that. It's just a sort of x86 detail. And that just worked. There's no special software required. We could just execute it, and it ran natively on the hardware. So that's a good sign, right? The next instruction was a no-op instruction. It's literally an instruction that doesn't do anything. And of course, that one worked because it doesn't do anything. This is almost too easy, right? Like these instructions are just executing and it's all just working. Sure enough, we hit another one and it just executes and it works because it's an add instruction and it just does an add. It's almost a little worrying because I said I've spent my entire career working on virtualization, and if you just run it and it works, then like, why am I being paid, right? This is why. When we hit our fourth instruction in this sequence, you get a failure. If you were running this as an application under Linux and you didn't have any kind of virtualization technology, your application would crash, and it would crash at this instruction. It's not really important what this instruction is, but it's what's known as a privileged instruction. So let's dive in a little bit more to what's actually happening here. All modern processors have multiple privilege levels. There's typically what's referred to as the supervisor mode or kernel mode. That's what your operating system is running at for drivers and device management. And then there's the user space mode. On the x86, this is often called ring 0 and ring 3, if you've heard that nomenclature before. So in order for virtualization to work, there's actually this formal theory. There's a really long thesis about it. It has a whole bunch of computer science jargon in it. But it basically says for a processor to be virtualizable, it must meet a series of requirements. And one of those requirements is whenever you encounter one of these instructions that are privileged, executing in an unprivileged mode, that it traps to a special piece of system software. This sounds a little complicated, so let's take a look at what this actually looks like in practice. So we've hit this instruction, it's thrown an error, the CPU can't execute it, and control transfers to a special piece of code called a virtual machine monitor, or a VMM. And this is really the component that is the heart of virtualization. The way that virtualization fundamentally works is using this VMM process. So what does the VMM process do? What is its job? What is its role? Well, when it encounters one of these instructions that can't be executed natively, it emulates the behavior of the instruction. In this case, the STI instruction changes a bit in a special register and then pushes the results onto the stack. So the VMM process takes over. It does that work. It fakes out the value of that register, and then it pushes it onto the stack, and it returns execution back to the processor at the next instruction boundary. And this is what that looks like. So after we've done the emulation, the next instruction gets executed natively by the underlying hardware. I mentioned that the VMM is the heart of the hypervisor. And within the sort of formal theory of virtualization, one of the other requirements given is that a statistical majority of instructions are executed natively and not emulated. A statistical majority sounds like kind of a fancy term. It's actually very qualitative. It just means that most. And generally speaking, on modern hypervisors, that's somewhere in the order of 1 out of a million or 1 out of a billion instructions get emulated. So the overwhelming majority of instructions are running directly on bare metal, and that is what gives you really good performance within a virtualization platform. Now, there's a really interesting point here, and this is one that gets subtly missed in a lot of discussions about how virtualization works. And that's that the VMM handles most things, but it doesn't handle everything. And this is really key to the way that the Nitro system works. So let's keep going. Let's keep executing instructions. Well, the next instruction we land on is actually an in instruction. And this one's slightly different than the STI instruction that we encountered earlier, because this is an instruction that interacts with hardware. So the in instruction is one of a handful of instructions that effectively sends messages to the actual hardware devices. So if you have a hard disk, for instance, attached to your computer, and the operating system wants to talk to it, it does it through these types of instructions that send little messages to the underlying hardware. The VMM actually handles the emulation of this instruction just fine, but there's some other thing that has to implement the logic of the device. So a really good analogy of this is an RPC call to a remote web service. If you have a microservices architecture that's a network-based architecture, your service is going to make RPC calls, and you have a certain amount of code that is handling those remote calls locally on your system, and it sends a message to another system. That other system might have almost an unbounded amount of complexity, right? It's an entire server. There's a whole lot of logic behind it. But from the perspective of that client service, it's just an RPC call. It's a relatively straightforward thing to execute, and all of the complexity gets hidden from you. Why is this important? The thing that is important is that while the VMM is executing a statistical majority of instructions on natively, all of device model logic, all of that back-end logic of that a sort of effective RPC call is implemented in software. That is not running directly on virtual hardware, at least in normal hypervisor systems. A modern hypervisor consists of a VMM and actually many different device models. I would certainly argue that most of the complexity of a modern hypervisor is in the device models. That's where all of the work you do for performance is. That's where all of the sort of heavy lifting is to get a really great experience. And that can be anywhere on the orders of low tens to even hundreds of device models in certain types of hypervisors. Now, a hypervisor also has a lot of other functions too: schedulers, memory managers, monitoring, logging, all of that kind of good stuff. The combination of all of those components is what I would at least typically call a hypervisor. It's a full system. It's more than just any of the individual components. As it turns out, this was the state of the art in 1974. That fundamental theorem of virtualization that I mentioned was a paper written back in the 70s. That was the state of the art. And it made a lot of assumptions, and it turns out that not a lot of those assumptions held true. The early Intel and AMD processors, so we're going to jump forward to 2006 when EC2 initially launched. The processors that were out there at the time didn't actually trap these instructions. They had weird behaviors, undefined behaviors when you encountered these instructions. And it's one of the reasons why, even though virtualization has existed since the 70s, it didn't really become popular until this time frame, because the hardware just wasn't capable of doing it efficiently. But there was a really interesting project that came out of the University of Cambridge called Zen. And they came up with a really clever solution around this problem of the Intel architecture not being virtualizable. What they did is they observed that a lot of people were using this open source operating system called Linux, and you can actually modify that code. So if you found all of the locations of those instructions that weren't trapping properly, you could convert them into interactions with the hypervisor that did trap, and that would allow you to make the virtualization actually work on this architecture. This is called power virtualization. This is the technology that EC2 launched with. It was hugely successful, and it was a really, really clever idea that's worked out really well. Now, that said, there's really no way that the Intel and AMD would sit on their laurels and not try to make this problem better. So of course, they introduced hardware virtualization technology. They basically made trap and emulate virtualization work properly on the processors. And not only that, they modified the mode that the system was running in such that the number of instructions you had to trap was much, much smaller, which really helps performance. This led to EC2 launching support for HVM. This allowed us to run workloads beyond Linux, such as Windows. And today, we actually don't support power virtualization-based guests on any of our new instance types because it's just slower. It's just not the right thing to use anymore because hardware has come a long way in the last 10 years. So let's fast forward a bit more. And let's go to 2012. So this is about the time of the first reInvent, about 5 years ago. EC2 is growing super fast. We're really, really interested in trying to get the most we can out of the underlying infrastructure and really trying to deliver the most value for customers that we possibly can. And so we asked ourselves, can we do better than this largely software-driven approach that has kind of become the standard within the industry? And where we really focused is on the device emulation, the device models, because the VMM is fairly low touch. And with modern virtualization hardware, the number of instructions you have to trap keeps decreasing year after year, and it's largely just handled by hardware today. On the other hand, device models are super challenging. So not only does it require a lot of complexity to implement these device models in software, they directly compete for resources from instances. So it's really a place that we thought we could do better. So we stepped back and we attempted to decompose the hypervisor, really look at it from this high-level component view, and start shuffling things around and trying to figure out a better way to arrange components. And so let's actually look at the journey. Let's look at how we've built this system over time. And we'll start with what I would consider to be one of the last non-Nitro platforms that we launched. And this is the CR1 instance. I suspect that most people either have never used it or maybe even have never heard of it, but it was actually a really cool instance at its time. So this is really one of the last instance types that we launched that used a more traditional virtualization architecture. So from a hardware perspective, you have a largely standard NIC, the sort of thing that you'd get in pretty much any server that you buy. It was a 10 gig NIC though, and super fast at the time. There was an HBA, a storage controller, again, largely an off-the-shelf component, and then some local drives for supporting instant storage. On the software side, our hypervisor architecture looked pretty much like what modern hypervisor architectures look like. You have a management partition. In Xen, this is often called a DOM0 or an IO domain. And then you carve off resources for the instances. It's actually really tough to get this architecture right. Finding the right balance between resources that you allocate to the management partition versus to the instance itself, making sure you're getting consistent performance, good quality of service, having good monitoring, good software update policies. It's all really difficult. It takes a lot of hard work to get a really good architecture. And I'm really proud of this architecture that we built. I think the most important thing to recognize in this architecture is that the instances don't have any direct access to hardware devices. Everything goes through that management partition, and it all goes through these software device models. That means every time you send a packet, every time you access an EBS device, every time you access instant storage, you're going through a bunch of software that's running on the same CPU that you're trying to execute your code on. So to begin the journey, we really looked at this platform and we said, okay, where are we going to start? So one of the things we could have done is we could have looked at this platform and said, we're going to design the perfect system, we're going to build it all from scratch, and then we're going to launch that. But that's not how we like to do things. We like to do small incremental changes. We like to get it in front of customers as quickly as possible. We like to get feedback because all of you teach us a tremendous amount about what works and what doesn't work. And then we like to iterate from there. And so we made an early decision to try this very iterative model to effectively rebuild the stack. We started with networking because networking is hard. When we talk about I/O, networking is just a completely different order of magnitude. You tend to talk about millions of packets per second, many gigabits of data transfer. It is the hardest problem, and if you're going to go after a really large, hard space, you can get a sort of false sense of confidence going after the easy problems, whereas if you start with the hard problems, you learn a lot really quickly. So where did we go? What did we end up with? We ended up with C3. And this is a super interesting platform. So C3 is where we launched enhanced networking. And this was, as Peter mentioned last night, C3 was one of our fastest growing instance types. We got really tremendous reactions from customers. Performance improved, especially on the jitter side, on the performance consistently, improved by almost an order of magnitude. And the way the actual hardware worked was really curious, and I was surprised when I actually first saw one of these servers. We added another card. So we got an off-the-shelf network accelerator card. We added it to the server, and we actually connected the standard NIC that was in the server to that accelerator card with a loopback cable. So if I was holding a C3 server in my hands right now, you'd actually see this little bump in the wire cable in the front of it. And it's kind of just a curious thing to look at, but it works really well, and it worked really well, and customers got really excited about it. The really key thing here is that on C3, you're talking to a piece of hardware directly. And that's really the key for how the Nitro system has evolved over time. So then what comes next? After we got all that positive feedback from C3, what was the next thing that we're going to tackle? And if you're going to sort of stack rank I/O in terms of what's hardest and what's easiest, storage is the thing that comes next by far. In this case, we looked at EBS. So EBS is particularly interesting because it's a combination of both what you think of as traditional storage and networking, because ultimately it is a network-attached storage. And so it's a little bit harder here because there really isn't, while there is a lot of network acceleration technology, storage acceleration technology, especially at this time, wasn't actually something that was commonly available. But we figured something out, and we built the system called C4. And this launched at reInvent, at the second reInvent, yes, in January of 2015. And again, this was a platform that supported enhanced networking, but that additional offload card we had was built by a company called Annapurna Labs. And this was a startup that we started working with. And the really interesting thing about Annapurna Labs is that they had this piece of hardware that would allow us to present remote storage as an NVMe device. So even though on C4, within your instances, you see a power virtual device, you see what's called a block front device. Under the covers, in the management partition, it's actually NVMe. So the same technology that is being mapped into a C5 instance, we've actually been doing it since C4. And all instances we've launched since then have been using that same technology. The reason that we kept the device model in front of the NVMe devices was simply that NVMe is a relatively new technology. We took a look at the driver ecosystem across multiple operating systems, and we just thought we needed to give it a little bit more time. So we kept that device model there for compatibility purposes, but we still switched to this architecture because it still delivered improvements in consistency. And most importantly, because all of the heavy lifting now was happening on dedicated hardware, we no longer were having to compete with resources in the management partition to support things like EBS. This allowed us to do EBS optimized by default, and it also allowed us to increase the amount of CPU that we offered to the largest instance size by 12.5%. So what comes next, right? This is a continuous process. We're going to keep going. Well, the next thing we looked at is having this standard off-the-shelf network card in the servers. While it was working really well, we knew we could do better than that. We knew we could build something better than that. And so that was the thing we set our sights on next. And that led to the X1 platform. X1 is a beast of a server. It was a lot of fun to build. It has 2 terabytes of memory. We've now launched our larger sizes, going up to 4 terabytes. We've pre-announced that we're going to build versions of X1 that go up to 12 terabytes. Like, these are just massive servers. The largest X1 instance type had 128 CPUs, just really, really beefy box. But it was also the first instance type that we launched that supports a feature called ENA, Elastic Network Adapter. And how Elastic Network Adapter works is super, super interesting. From a customer point of view, from an instance point of view, it's enhanced networking, but you use a different driver. It's really not that different. You get pretty much the same experience as you got with C3. You're just using a different driver. But under the covers, things are very different. So instead of talking to a off-the-shelf network adapter, everything is going to this Annapurna device. And this is actually the first Nitro card, the first true Nitro card. And that's because around this time, we had actually, we liked working with Annapurna so much that we acquired them and they became part of the Amazon family. And because of this, we worked with Annapurna to build a custom ASIC that could support not only just EBS offload, but also full network device offload. So this is super exciting. X1 was a really great platform for us, but we're still not done. One of the things I'll point out here, though, is that we've been operating on a pretty steady cadence at this point of about a year introducing a new component of the Nitro system. And not surprisingly, it's going to keep going like that. The next thing we set our sights on was instant storage. So something really fascinating has been happening in the storage industry in the last few years. So for many, many, many years, storage was all hard drive based, spinning disks. And while density of hard drives have increased over the years, performance of hard drives really haven't increased significantly because there's just law of physics problems with how fast you can spin rotational media. If you spin it too fast, it's just going to shatter and destroy the server. So there's just fundamental physics limits there. However, in the past maybe 5 years or so, SSDs have become super common. I suspect everybody's laptop today has an SSD in it. That was not the case 5, 10 years ago for sure. Another piece of technology is coming along too, called NVMe. And that increases the performance of SSDs substantially. So for the first time in probably 20 or 30 years, we're actually seeing storage performance increase at a pretty steady rate. And so we had to figure out a solution for that. That brings us to the i3. And this is another platform that is really just a beast. So the i3 has, besides having a lot of memory and CPU, it actually has 8 NVMe drives. The i2 platform, which was the predecessor to i3, also had a lot of SSDs, and it supported up to 385,000 IOPS combined in the largest instance size. I mean, I can tell you firsthand, getting a software device model to drive that kind of performance was a lot of work. There was a lot of late nights getting that performance to be the best it possibly could be. And we were really, really proud of that particular platform. But for i3, we set our targets higher. And what we actually shipped was able to support 3 million plus IOPS on that hardware platform. How we were able to achieve this is that there's not actually a software device model involved. When you launch an i3 instance, you are having hardware mapped directly into that instance for those underlying drives. And that hardware is backed to a Nitro card, to a Nitro chip. And that chip is doing all of the work of monitoring the drives, encrypting the data on the drives, and implementing quality of service to make sure that we're delivering a consistent experience. So obviously the next question is what comes next, right? So it really comes down to what's left. And the only things that are left are the hypervisor and the management partition. So that's what we set our eyes on next. And this is what led to C5. So on C5, we've made a number of changes, starting with the underlying VMM. Now, I mentioned before that a hypervisor consists of a VMM and a bunch of device models. But now that we've moved all of the device models to custom hardware, custom ASICs, we really don't need that anymore in the hypervisor. that gives us the opportunity to make a really dramatic simplification of the software stack. And as part of that, we really looked at what is the best VMM that we could provide for this new environment. Now, one of the things about a VMM is that the work it does, there's really a right answer. Like a lot of software, there's not a right or wrong answer. There's a right way to emulate an STI instruction. There's really only one right way. So the choice of VMM isn't nearly as important as, say, the choice of device models. But that said, we wanted to find something that was small, that was well contained, that we could sort of shape in the way that we needed to. So we picked KVM as a base here. But while we picked KVM as a base for the VMM, when people generally think about KVM, they think of a much larger software stack. They think of things like libvirt, maybe OpenStack. They think of things like QEMU. We're not using any of that software here. We're really just using the fundamental KVM kernel module, and we've made a number of changes to that too. The other thing that we've eliminated in this picture is that management partition. Because once you've gotten the really hard things out of the way, once you've gotten the heavy lifting of the device models, it would be sad to dedicate cores on the server just to do logging, right? Like those are resources that we should be able to make available to customers. We were able to achieve this by actually moving the really required monitoring and management functionality on the platform to one of these Nitro cards. And that allowed us to deliver 100% of the resources of the underlying server to the instance. So when you run a C5 18x large and you see 72 vCPUs within your instance, that's because you have all of the CPUs on the instance. There aren't any that we are reserving to run our software or anything like that. You truly do have all of the underlying resources in the server. We like to talk about the Nitro hypervisor as a quiescent hypervisor. So what that means is that unlike a traditional hypervisor where there's a whole lot of stuff running in the system, we really try to have the Nitro hypervisor only run when the VMM truly needs to run, when you hit an instruction that has to be emulated or there's some kind of behavior that has to be implemented for it. That means that if you're just doing CPU work within your instance, if you're just crunching numbers, you should be able to run uninterrupted as long as you want to. The next very exciting thing that comes from this, though, is that once you have this very simple hypervisor that really is just taking care of the role of the VMM, is that hypervisor really even needed anymore, right? Because all of the interesting work already is offloaded to hardware. Can you just talk to hardware directly? And this is what allowed us to build the i3.metal instance. There's another component we had to add. This is the Nitro security processor to make sure that we could deliver bare metal in a way that was secure and delivered all of the kind of experience that customers would expect. A colleague of mine, Matt Wilson, is going to do a talk at 4:40 where he's going to go into details about how this all works. So I'll save that for his talk. The final thing I wanted to mention in the context of the sort of evolution of the EC2 virtualization stack is VMware on AWS. Like I mentioned, we love getting feedback from customers early. And for this new bare metal platform, we, of course, wanted to get customer feedback as quickly as possible. And this is why we worked with VMware to build the VMware on the AWS offering, which allows us to offer VMware within EC2 without using nested virtualization. The important thing here is that whether you're running on C5 and M5, i3.metal, or even VMware on AWS, you're using the same fundamental technology that we've been building into our platform since 2012. When you get an NVMe drive on an i3.metal, it is the same NVMe drive that you get on an i3 16x large, and it'll be the same type of NVMe drive you'd get in future instance types that support instance storage. So to summarize a bit, the Nitro system overall consists of three main components. The Nitro hypervisor, which is our lightweight quiescent hypervisor. the Nitro card, which effectively does all of the device model work, but it does it in dedicated hardware that's purpose-built for EC2. And then the Nitro security chip, which is what allows us to deliver a really high assurance of the underlying platform and allows us to offer bare metal as an instance type. So finally, I wanted to, before I open it up to questions, I wanted to cover a couple common things that have come up since we've announced C5. One of the questions we get a lot is, will the existing AMIs continue to work on Nitro-based hypervisor platforms? The answer is yes. Most ENA-capable AMIs will just work because ultimately we're using the same underlying technology as we've used on previous platforms. So if something works on an i3 or something works on an R4, then it'll work on this platform more or less. There are some corner cases, but for the most part, things just work. Another common question we get is, well, what about my applications? Do I need to retest? Do I need to recertify? Because people generally think that, a new virtualization stack is a big change. But really, the things that are the most important aspect of the platform, the device models, they've really stayed the same. So for the most part, applications will work exactly as they do on other instance types, except you get more resources. There are some applications we've found that rely on undocumented behavior of EC2, specifically for detecting things like, am I running under EC2? We actually document the right way of doing that, but people build things the way they build things. So there may have to be some adjustments there. And then finally, what about future instance types? Or will all new instance types be Nitro-based? All instance types since C3 have had some form of Nitro technology in them. And so it's safe to say that all new instance types will continue to have Nitro-based technology in them. In the fullness of time, we do expect to use the Nitro hypervisor on all instance types. However, in the short term, we'll evaluate it on a case-by-case basis, and you should absolutely expect that we will launch additional instance types that use the Nitro system, but continue to use the Xen hypervisor if it's the best thing for customers. And so what's next? Well, I'm actually not going to tell you, because then I won't be able to speak about anything at the next year's reInvent, so you'll have to wait until then. But there's some trends that I hope that you see so that you can kind of guess as to the sorts of things that we're going to be doing. So the first thing is we're going to hardware offload the things that make sense. The second is that we're going to innovate incrementally. So we're going to keep introducing relatively small changes into the platform bit by bit so that we can get feedback from customers and we can iterate quickly. And that's actually the thing I'm most excited about with the launch of C5 and M5 and i3 Metal is to hear from customers about how it works for them, how they like it, how it sort of compares to previous instance types, because that's ultimately the thing that will really determine what comes next for us. We'll listen to you, and then we'll use that to decide the next things that we tackle. So that said, thanks everybody very much, and I'm more than happy to take questions if anybody has them. Go ahead.
Test, test. So I noticed that the new C5 and M5 instances, the smallest class is the large. Are you going to be doing the small and mediums of those as well?
Yeah. The question was, for C5s and M5s, are we going to do mediums? Are we going to do things smaller? We're definitely looking at instance types that have less compute associated with them. It's really something that we'll respond to based on what customer demand is. So for platforms like the M3 Medium, the way it shares CPUs, we don't really, it's not great. We actually think that things like T2 share CPUs in a significantly better way. So I think that's the kind of interesting conversation to have is if you're looking for something smaller, generally we think T2's the right answer for that. And so that's just an area that we'll have to iterate on.
Thank you.
Yeah. Hey, Brendan.
Hey. Interrupts.
Yes. OK. One of the things that's new about C5, and I didn't really get into details here, when a piece of virtual hardware wants to send a message back to the CPU, it does so through an interrupt. And in traditional hypervisors, the interrupt actually has to bounce through the hypervisor, and it's a fairly heavyweight process. So C5 actually makes use of posted interrupts and direct APIC virtualization. So what that means is that in most cases, the interrupt goes directly into the guest and bypasses the hypervisor and is entirely hardware accelerated. And over time, this is the kind of thing that you should just expect to see more and more of, is that you get pretty much direct hardware access.
Hi.
Hello.
Existing instance type have a AWS PV drivers package installed, right? So what is the equivalent of CV5, the new instance type?
Yeah. So the question was, existing instance types have PV drivers installed.
By default.
What about the new instances, or the new AMIs?
So is it plain KVM drivers, or we have something equivalent from AWS?
So the only drivers that we actually require are NVMe and ENA.
Okay.
And so it turns out that most AMIs today already have NVMe because that's what we launched i3 with. And so we've already done a lot of the work to make sure that NVMe is available in all of the popular AMIs. And then with X1, because we launched ENA with X1, we again went through and worked with our partner ecosystem to ensure that all the different AMIs had ENA drivers in them too. So the expectation is you don't need to add any special KVM drivers to your AMI. If your AMI worked on i3 or R4, it should just work on C5.
Okay. So the EC2 config service still valid in new instance types, right?
Yeah, the question was the EC2 config service, does it still validate new instance types? I actually don't know the answer to that question. I'm not super familiar with the EC2 config service, so I have to go back and get an answer for you from the team.
Thank you.
Yeah.
Yeah, is Intel SGX supported on the Skylake instance types? And if not, what's involved to do so?
Sure. The SGX is not supported today on server-grade Skylake processors. So there is not a server-grade Skylake processor today that supports SGX. So that is something we're looking at. We're working with Intel on, but we can only deliver it as fast as it's available for the types of servers that we build. But yeah, it's a super interesting feature. We're absolutely paying attention to it. We just need the hardware to be available. So it's not supported on C5 today.
Hi. So for the EBS and for the web traffic, so the kind of traffic has been separated for guarantee all the same line for the network port? Yeah.
So I believe the question was, has the EBS traffic and the networking traffic been separated? The answer is yes. They are actually, it's a separate traffic stream. It's actually a separate connection to the physical network. And so there should be no interaction between, if you're doing a lot of networking performance, it will not take away from your EBS performance in any way. It's actually physically separated hardware. And this is really one of the advantages to the Nitro system, is that we know every server we build is going to have VPC networking. We know every server is going to have EBS, and therefore we can dedicate specific hardware to those functions and make sure that it's always available.
So just a quick question on the current generation of P3 instances. Is that Nitro-based or is that not Nitro-based?
Yeah. All of our instances have some type of, or all of our instances we've launched in the last 5 years have some type of Nitro capabilities. But P3 is still based on the Xen hypervisor.
Okay. Got it. Because I would figure that if you're doing a lot of profiling where you want to both profile the GPUs as well as a lot of the CPUs and you have very heavy workloads, you might be interested in this type of hypervisor. Yeah, absolutely. We're absolutely looking at what are the next platforms that make the most sense to introduce the Nitro hypervisor. Yeah. If anybody has favorites, love to hear feedback, and it's part of the way we prioritize these types of things.
So I'm assuming you're using something like Intel VTD, like direct I/O to isolate. So does that mean you're physically having a separate Nitro card for each guest?
Yeah, so the question was, we're using Intel I/O virtualization technology to actually separate or to assign the devices into a guest. And does that mean you're using separate physical devices? It's complicated. So at a really high level, you don't need to have physically separate devices. What you need is to have separate PCI endpoints. So a single physical card can actually have many different PCI devices on it. And so part of the secret sauce of the Nitro controller is its ability to do some of that kind of magic. So the answer is sort of, but not in the way you would think.
So since you bought the company that is creating that card, is it available for sale for other people, or is that Amazon's secret sauce now only?
This is ASIC that we've developed specifically for EC2. It's really designed for EC2. I'm not even sure it would make sense outside of EC2. But as always is the case, we listen to customers, and if we have a lot of customers ask for things, like we'll always consider building it. So if we heard a lot of demand, we'd certainly consider what we could do to satisfy that demand.
Thank you.
Yeah.
So you have cut off the Verdejo component from the hypervisor?
Yeah, were you asking specifically about VirtIO or just VirtualIO?
VirtualIO.
Okay, so VirtIO is a type of paravirtualization technology. It's similar to the Zen ParaVirt drivers that we use within EC2 today. We did look early on. I actually was heavily involved in building VirtIO in a previous life. So we, of course, looked at VirtIO. But to be honest, I actually think that NVMe and ENA are just better device models overall. We started designing VirtIO 10 years ago. And there's just so much that has been learned in the industry over that last 10 years about how to do high-performance I/O that I honestly think that NVMe and ENA are just better interfaces. So no, we don't do VirtIO. We do NVMe and ENA.
Yeah, you use NVMe and ENA. That's great for the performance. But the weakness of this solution is that the weakness of this solution is that you have to install the driver and into the guest. And so some guests would like or don't like this way. So the VirtIO, the advantage of VirtIO is that it's a standard.
Sure, yeah. So the observation is that VirtIO is a standard, so the drivers are widely available. I think the same is true certainly for NVMe. In fact, I think a lot of folks' laptops have NVMe drives in them today. My laptop certainly does. But yeah, this is an area where, like everything else, we're really open to customer feedback. So if there's another type of device model that customers really prefer, it's absolutely something we would look into over time.
Yeah, in current solution, there's another problem. Is just that you use SRIOV. That would involve another problems, right?
No, I mean we could if it was the right thing to do, we could certainly do it.
Okay, so for the Gosset devices, for example, the keyboard and the VGA devices, have you cut off the QEMU logic entirely?
We don't use QEMU at all.
You don't use it at all?
No.
So you don't support the traditional keyboard and VGA?
We do.
You do?
We just don't use QEMU.
So you just don't use QEMU, right?
That's correct.
So you use other kind of, for example, Kevin tools, such kind of tools?
Yeah, this is all part of the Nitro system. So we've built special things into the Nitro system to support this, but it's not based on QEMU.
Okay. Thank you.
Yep, thank you. Oh, sure.
Is the level 3 cache shared over all guests? Or is it really split up across multiple
Sorry,
guests?
could you repeat that, please?
The level 3 cache of the CPU, is that shared across all guests running on the same CPU, or is it really split up?
Sure. The question was whether the level 3 cache is shared across all guests, whether there's sort of isolation there. It's a very specific question to a particular platform. And so there are a lot of technologies today, like Intel's cache allocation technology, that you can use to sort of add quality of service to cache access. No matter what you do, the L3 cache or the LLC, it has to be shared, right? It just has to be shared across cores. But there's different types of quality of service features you can implement to ensure that you don't get noisy neighbor problems in your cache. We use a lot of different types of quality of service mechanisms to ensure that customers are getting consistent performance. If you're seeing problems that you suspect are like LLC-based noise, very happy to dive in and help you understand it. But generally speaking, yeah, it's unavoidable to do some type of cache sharing.
Except using an instance at large size.
Well, no, obviously the large sizes, any of those sizes where you're using the entire socket of the underlying server, you have that entire socket. It's totally on you. Yeah.
So 2 questions. So in testing sort of for network appliances, usually we've seen on larger instances some kind of PPS caps. Does C5 have the same thing?
There's always a limit in terms of how much performance any particular instance type can provide. We actually have a feature that we introduced with actually C5 that some of the folks from the EBS team have been talking about called EBS Burstable Performance, I believe is the name we ended up going with. And that allows smaller instances to get larger bursts of performance. But the largest instance sizes, they get as much as the platform can deliver. So generally, yeah, you will see like a fixed amount of performance in the largest instance sizes, because that's what the underlying hardware can deliver.
But on the network side you're talking about?
Sorry?
On the network side?
Yes.
Okay.
Yes.
And second one, for custom armies that don't have ENA, I know I could have already figured this out, but what's the level of work? I mean, if we have just the standard Intel SRIV DPDK, and now we need to enable ENA.
Okay. So the question was about DPDK support for ENA. We actually have ENA drivers for DPDK. They're in upstream DPDK. Okay. So generally speaking, porting over to use ENA instead of the Intel 82559 is relatively straightforward. We're definitely happy to help out. This is the kind of stuff we really enjoy doing. I certainly enjoy doing it. Okay. So if you run into problems, there's documentation. There's actually ENA documentation as part of dpdk.org. Okay. But you can always reach out, and we'd be more than happy to help out.
Okay, cool. Thanks.
Yeah. To the side.
Yep. Seeing as the NVMe drives are ephemeral, is there any work being done to like rapidly propagate them with data similar to like an EBS snapshot?
Sure. So for C5, you get NVMe both for EBS, and then C5 doesn't have instance storage, but i3 does have instance storage, and that's NVMe. And those drives, they're not ephemeral in the sense that as long as the instance is there, those drives are there, right? So they behave exactly like a drive would behave in a normal physical server. That is a feature, the feature request of having instance storage back up to an EBS volume is one we've heard from a number of customers, and it's definitely something we're looking at. But like all things, it's a matter of figuring out when's the right time versus other priorities. So, but yeah, it's definitely a request that we've heard from a lot of customers.
Thanks.
Yeah.
So with C5 so close to bare metal, why should somebody choose bare metal over C5 or the other way around?
That's a great question. And in a lot of cases, just using the largest instance size is not a bad thing to do. In fact, there are some legitimate reasons why you should use a virtualized instance over a bare metal instance. One of them is that there are details of the underlying hardware that become visible and are more likely to change over time. So one of the great things about virtualization, one of the great things about cloud, is that generally speaking, your application doesn't need to worry about changing DDR speeds or slight differences in manufacturing model of hard drives. You don't have to worry about that on this type of server, the PCI address of a device changes, and so Windows throws up an error because it's a new driver that has to be installed. So there's a lot of really good reasons to use virtualized instances. And generally speaking, if you don't have a specific reason to use bare metal, I would suggest you use a virtualized instance. I just think they're easier for most things. But there are features that are really hard to expose in a virtualized system. A good example of this is performance counters. Performance counters, at least a number of performance counters, the hypervisor, if it tried to expose those directly to the guest, either would introduce like really subtle sort of information leakage, or it would just impact performance too much for it to be practical. So if you're trying to run something like vTune, or if you want to do really deep like perf work on an instance type, bare metal is actually super useful for that. The other thing where bare metal just makes a whole bunch of sense is if you want to use virtualization. So if you're interested in running things like clear containers, which is a new container technology that actually runs a container within a virtual machine, Or even if you just want to run a KVM development box to carve up a server in the way that you'd like to carve it up, that's a perfect use case for bare metal. And if you really want to hear more about it, I really suggest attending Matt's talk at 440. He'll go into a lot of this too.
Thank you.
Yeah.
With the success of the Nitro platform, I was wondering if Amazon's seeing like increased internal usage of hardware acceleration for other services.
Sure. So the question was, are we seeing more internal usage of hardware in other services, given all that we were investing here? And I think you've seen a lot at reInvent about the intersection between hardware and higher level services. So one of the things that I thought was super interesting was all the stuff that Matt Wood was talking about around the P3 instances and how much that's helped machine learning workloads and all the sorts of things that you can do with that. So yeah, we try to look across the entire company and see where we can use a combination of hardware and software to solve problems that customers have.
Right.
So, yeah.
Well, I guess I meant like not commodity hardware like that we could buy from NVIDIA,
Sure.
but stuff that you're making custom.
Yes. We will continue to build custom hardware where it makes sense. It's obviously an area that there's a lot of investment to make, or there's a large upfront investment to make in building a custom ASIC. It's not something you do lightly. So you really have to be careful about like whether you have the right use case for it. But yeah, it's something we're looking at. I don't have anything I can talk about today, but yeah.
Almost continuing on that thought, so what is the business value in terms of, say, keeping 4 to 6 CPUs for doing some of the overheads on the host OS versus investing so much money and having a dedicated chipset next to each server?
Yeah. So the question was, what's the business value? So ultimately, I think it's answered by the fact that when we launched C5, it was cheaper than C4. And the reason for that is because we've been able to drive cost out of the platform with this approach. So that's really the answer to it. Like, this is a mechanism that we think allows us to build more cost-efficient platforms, which ultimately means that we will be able to lower prices for our customers.
We have a custom army. I hit 2 issues that I've found so far. I'm rebuilding at the moment and hoping it'll then work.
Okay.
One of which was having cut the NVMe drivers out at some stage in the history because we didn't think we needed them.
Okay.
And the other is using device names for disks in the boot menu. Are there any other things that we should be looking at to avoid having to iterate too many times?
Okay. So and this is going to have to be the last question, I think. So I'm happy to take questions outside, though. The observation was that the device naming has changed with C5 because of the use of NVMe drives for EBS. And obviously, you need NVMe. So if you build an AMI that doesn't have it. You hit the 2 big ones. We actually have cloud init scripts that do device naming specifically to give compatibility. So one of the options is to get to the latest cloud init, and then you will get the old names like you'd expect. The only other thing that people have run into in this space is any kind of checks that they have in their startup to see if you're running under EC2. So we have a very specific documented way of doing that using the UUID that comes from DMI information. But some people have done things like check to see if you're running on a specific version of Zen, things that would have broken eventually anyway. So that's the other area we've seen. But other than that, things largely have just worked.
Thanks.
All right. I'll take one more question, and then that really has to be it. Go ahead.
Yeah. From my understanding, under the bare metal situation and the C5 situation, the backend card should be entirely SIM, right?
Should be
SIM.
Yeah, yes, you see the entire card. Well, you see the Nitro card.
Use the SIM card.
Yes, it uses the same card. It'll look exactly the same.
Just curious from slides that there's some function different.
Nope, they look exactly the same. So.
But for bare metal, if you can only support one hardware to one customer. For example, some customer need 8 CPUs, some customer need more CPUs. How can you solve this problem?
Very carefully. Yeah, this is part of the work that has gone into building the Nitro system. There's a lot of custom hardware in the platform specifically to enable this. Yeah, it is a really interesting challenge.
So you have to prepare a lot of hardware platform.
Sorry?
So you have to prepare different kinds of sites.
You have to build ASICs.
Okay, thank you.
And that's exactly what we've done here.
Yeah, that's a problem.
All right, thanks everybody. That's all the time I have.